course, you recall that solution is a solute dissolved in a solvent. Together they make the solution. And in order to make a solution, there are three commercial sources, well, not two commercial sources, one laboratory source of reagent to make solutions. Of course, manufactured, and these include solids, liquids, and lab stock concentrates. When we talk about solids, what we're talking about is ordering a reagent from a manufacturer, and when you get it, it's in solid form. And typically it will come to you with an assay sheet identifying its purity, its structure, and also include a material safety data sheet, as we used to call it, as a safety data sheets now. But anyway, the MSD sheet for the substance should be reviewed. And if you work in chemistry and start working in a laboratory, whatever you work with, if you're not familiar with it 100%, review the material safety data sheet or a safety data sheet that comes with the chemical. It has all kinds of basic review information of how to use it, how to dispose of it, how to protect yourself if this has any hazards associated with it. And of course there are manufactured stocks that are come to you in liquid form, especially say strong acids and concentrated acids, manufactured concentrated liquids, liquid concentrates. I should have said that. Sounds better. Manufactured liquid concentrates. And now a lab concentrate is where you make your own solutions at a high concentration. For example, hydrochloric acid comes at about a 12 molar, very hazardous material to work with, and it's very dangerous, and you have to take a lot of precautions. So, but if you dilute it to say 8 molar or 6 molar type solution, then you don't have to take as much precaution, and it doesn't pose the hazards, which I'll mention here in a little bit, that the system would involve. So this lab concentrate kind of defines itself. You make a concentrate and then use for making diluted samples. So you're going to use them to make diluted samples and then use them in your research or whatever you use them for. So those are the three sources we need to talk about. And the central question here in making any of this solution is how much of the source do I need to make my solution? So So this is the essence of what I'm trying to teach you right now. How much solid, that is, how many grams do I need to put in a bucket to dilute up to whatever volume I need, or how many milliliters of the concentrate do I need, or how many milliliters of this concentrate do I need to take and dilute to whatever I need. So that's the essence of what I'm trying to teach you. Now, there's some simple formulas that are used to determine these amounts. They can be derived from basic definitions of molarity and concentration terms, and from solution terms that you studied in Chem 1. So, what I want to share with you is a method of preparing solutions that's very straightforward and has a broad applications to whatever research system you're working with. Now, of course, the idea is to transfer needed amount of solute into mixing container and follow with solvent up to but not to exceed needed total volume. So graphically, that was amount of solute, and you transfer that into your mixing container, whatever it is, and then you bring needed volume. So you have solvent plus solute mixed up to, but not to exceed the needed volume. If you put, say if you're making a 100 milliliter solution, you put 2 grams in the container and add 100 milliliters, your final solution is to dilute. But if you put 2 grams into your container and add solvent, say water, whatever, up to and stop at 100, that's making the solution, is what I'm trying to get to. So it's a procedural thing, but it's very important in the accuracy of preparing solutions. So next is, how much do I extract from the container of solid? How much do I extract from the container of liquid? And then how much do I extract from my lab stock? So there's some simple formulas. Solutions from your manufactured solid stock. And it's a very straightforward formula. Again, it can be derived from definitions of molarity and solution concentration and so forth, but it's like this. Grams solid needed equals molarity, and I'll itemize these in a minute. Molarity times volume expressed in liters times the formula weight of the solute divided by your purity factor, where M is your molarity needed, volume is liters of solution needed, VL. Of course, F weight is formula weight of solute, and PF is your purity factor in decimal fraction form. So it's more of a practical need. This is a problem that, of course, reflects preparing a solution. So let's say, for whatever reason, you need to prepare 250 milliliters of a 2.35 molar sodium hydroxide solution, and AQ means in water as a solvent. solution from a manufactured stock that's 98% pure and has a formula weight of 40 grams per mole. Now, the purity factor typically is found either in the MSD sheet or the reagent assay that may be taped to the bottle, and it'll say assay, and it'll give you a percentage purity for that substance. So, starting with this as an objective, what is the idea? Okay, how do we go about it? How much of the sodium hydroxide do I need to extract from the solid, manufactured solid, transfer to the container, and you add solvent up to, but not to exceed, 250 milliliters. So we use the expression grams solute is molarity times volume in liters times formula weight of the solute divided by the purity factor expressed as a decimal fraction. And so that, of course, would be, I should have spelled that, grams. So that is, the molarity needed is a 2.35 molar solution. Now, molar solution is moles over liters. That's the definition of molarity, moles per liter. Moles of solute divided in a liter of solution. The volume has to be expressed in liters, so that we would put that 0.250 liters. Right there, formula weight is given to be 40 grams per mole. And the purity factor in decimal would be 0.98. So it's, in essence, dividing by a fraction like that scales it up to just a little bit higher than just absolute amount. And if it's a pure, 100% pure, like you'll work with a substance called a potassium hydrogen phthalate, well, that's 100% pure. So you divide by 1 in a case like this. So you can see where the liters will drop out, the moles drop out of the term molarity, and you're left only in grams of substance. This one has no units in it. So in essence, applying the idea to the formula given, says we need 23.98 grams of solute stock and transferred into the mixing container. Add solvent up to, but not to exceed, the 250 milliliters. Now the issue is, this is the theoretical amount needed, but for you to measure out this much, well, okay, so you stay there all day and you get 23.98 grams. Trust me, no matter how hard you try, the nature of things will not give you exactly the 2.35 molar sample. I'll show you in a minute how to make that adjustment. But let's say you just put in more or less than the 23.98. How do you go about calculating the concentration of sample? If you did hit 23.98 and dilute to 250, you would have 2.35. But assume, for argument, amount of sodium hydroxide solid used was 24.73 grams, and you diluted that to 250. So we're looking for the solution concentration. We know we should be around the 23.98 to be perfect, but let's say we got sloppy and we added 24.73. All right. So what this tells us to do is convert to the concentration. Well, concentration in molarity terms, and use a capital M, is moles of solute divided by volume of solution expressed in liters, is what the definition is, moles per liter. So we have 24.73 grams, so we need to convert that to moles. How do you do that? Divide by formula weight. So moles of solute, which is our sodium hydroxide in this case, is 24.73 grams divided by 40 grams per mole. And so we see the grams will drop out, and this gives us 0.618 mole of sodium hydroxide in solution. Now the volume, of course, solution, final, is of course needs to be 250 milliliters, but should be 0.250 liters. So this is applied to this definition, and so the molarity of the sodium hydroxide, and I showed you this yesterday briefly, brackets NaOH. This means moles per liter concentration, and it will be used extensively in going forward in the course. Is equal to, well, the moles is 0.618 mole divided by 0.250 liters. And we have a 2.47 molar NaOH aqueous solution. Right there. Now, let's say you have to have it at a 2.35 molar. And you need to dilute that from 2.47 to 2.35. There's a simple formula that will allow you to calculate the amount of water that you would have to apply to that to get to dilute it to the final volume. If you're limited to 250 milliliters, then how many milliliters of the concentrate do you need? So let's assume limited to 250 milliliters total volume. Total final volume. Move this up here. Then how much of 2.47 molar concentrate would be needed and diluted to 250 milliliters total volume, right here. It's called the dilution formula. Molarity times volume of the concentrate equals molarity times volume of the dilute. Or in simple terms, molarity times volume of the concentrate equals molarity times volume of the dilute. Diluted sample. Now, from what we have the molarity of the concentrate, but the question is, how much of this concentrate do we need to dilute to achieve what our final objective is? Over here, we have a 2.47 molar concentrate, and that's set equal to what we need, which is the 2.35 molar diluted sample, and we need 250 milliliters of it. Now, one rule, and this only applies in this case, if both sides are the same units, then you do not have to convert the molarity the volume term to liters. If one side's moles and the other side's in molarity volume terms, yeah, you'll have to convert that volume to liters to work that type of problem. We'll see some coming up here as we move forward. So this is your unknown. We just put volume in milliliters needed right there and solve for volumes, milliliters of concentrate needed right here, and that's 2.35 molar needed, and we need 250 milliliters of the diluted divided by the concentrate. Molarities drop out, and when the calculation will leave us in milliliters. And so I need 237.9 milliliters plus solvent up to 250 mils total final volume, like that. So what have I just given you? One is how to make a solution from a solid stock and how to adjust that stock concentration if you shoot above or below. If you shoot under it, well, of course you can shoot over but not under and still use the dilution equation. And then use the dilution equation. Molarity times volume of the concentrate equals molarity times volume of the diluted sample. And then solve for what you need in this case. So solution for manufactured liquid concentration is essentially the same thing, except when you receive your reagent from the manufacturer, it's in liquid form and is in a high concentration typically. Example is high acid concentrations, acid or base concentrates. For example, hydrochloric acid usually comes as a 36% by weight solution in water. It's a very, very strong solution and has a specific gravity, you will need that number, equal to 1.14, which since it's water solvent, equals the density of in grams per milliliter, 1.14 grams per milliliter. So here you have this bottle of acid, very strong acid. The question is, how much So just as we dealt with the solid stock, how much do I need to extract and dilute up to, but not to exceed the appropriate needed volume? Well, the formula is essentially identical except for the specific gravity term. And it looks like this: milliliters of stock is equal to molarity times volume needed in liters times formula weight of whatever solute you're dissolving, like HCl 36 grams per mole. Its purity factor is whatever it's delivered at, say, 36%, so it's 0.36. So it's just like the first formula we used, but it's also divided by the density number or specific gravity number in grams per milliliter. And so all of the terms will drop out of this except the milliliters term. So this gives you milliliters of stock you need to extract, transfer to the mixing container, and then dilute to the final volume. So basically it's the same kind of problem. You're given the task of making 500 milliliters of a 5 molar hydrochloric acid solution from manufactured stock that is 36% active in solute, that is the HCl, with a specific gravity of 1.14. Now, the specific gravity listed on the assay will only say 1.14. It won't say grams per mil. You have to remember that if the solvent is water, that is also grams per mil density of that stock. And here's your formula weight. Anyway, the milliliters of stock, HCl 36% needed, will be again molarity times volume in liters times formula weight divided by your purity factor, also divided by the specific gravity in grams per mil. So in this case, we need a 5 molar solution, and we need 0.500 liter. Formula weight's 36 grams per mole. A purity factor is 0.36 because you've got a 36% active solution. And specific gravity is given as 1.14, and HCl always comes in water, so you apply a grams per milliliter. And so now this is again moles per liter in the molarity. So liters will drop out, moles drop out, grams drop out, and so you're only left with milliliters in this case. So this calculation says we need 219.3 milliliters of 36% HCl mixed in enough solvent to make the 500 milliliters. Now, what you did in the procedure for making the solid into a liquid, you don't use in here. If you put 219 milliliters of 36% HCl in a container and you start pouring water on it, it'll blow up in your face. This is a reagent that ionizes so fast and generates so much heat that it becomes dangerous to make solutions in that format. So what is typically done, add acid to a quantity of water less than total needed, then dilute to needed total volume. Because if you dilute it first in a quantity less than what's totally needed and then finish with diluting to the mark, as is frequently referred, then you will avoid that danger of flash is what will happen. And so essentially that's the approach. Some people say, remember A and W root beer. Acid to water, then dilute. So keep that in mind. Now, yeah, if you overshoot the amount when you make it, just go to the dilution equation and cut it back to what's needed. However, working with solutions affords the many times more accuracy than working with solids. Okay. So if you make an HCl solution that's 5 molar and you've got 500 mils sitting on the shelf in storage, and your research may use only 100 mil of a 1 molar or something like that. Well, that's easy to draw and calculate. Just use the dilution equation to make your diluted samples and use them in your experiments or your research that you needed. So that's a synopsis of solution preparation.